Okay, welcome to the final lecture here. So we are into chapter 13 and we're going to finish it, or wherever we get to, I suppose, by the time we're done. Let's hope so. Let's just hope for the best. So chapter 13 is carbohydrates, all of our fine bread products, right? So carbohydrates, obviously, as we talked about last time, are made out of carbon, hydrogen, and oxygen. They are sometimes referred to, obviously, as sugars. We got into sort of a couple of things last time. We got into chiral sort of carbons. And chirocarbons are really carbons that have, you can see my creativeness is really bad right now. It has 4 different groups attached there, each one represented by a number, and that would be a chirocarbon. A chirocarbon means that, for example, our chiral compound, if you put it up to a mirror and you take its image out of the mirror, it will not superimpose. So it cannot superimpose on each other. That's different than, say, a achiral, where, you got at least 2 groups that are the same. And in this case, these 2 groups would be the same. If you take the mirror image of that guy, you can rotate it about and get it to superimpose on each other. Okay. We also talked about sort of the last chirocarbon, for example. In a compound, and we'll say this is the last chirocarbon. If that OH group is on the right-hand side, that is what we sometimes refer to as being D. And obviously, if our last chirocarbon there, the OH group there, is on the left-hand side, it is an L sort of designation. We finished up talking about sort of monosaccharides or carbohydrates and sort of the functional groups that we typically will see with these guys. And there's really 2 sort of organic functional groups that we see. We see the aldehyde group, which is sometimes referred to as an aldose, like an aldehyde. And we also do see up on top there the ketone type group, which is sometimes referred to as a ketose. So based on sort of which group that we do see, and these guys are usually up on top of the carbohydrates, we will either call it an aldose or a ketose. We could also classify the carbohydrate based on how many carbons there are. So like pentose, hexose would be 6 carbons that are involved as well. We also saw that you can have, more than 1 chirocarbon, for example, in a carbohydrate. And obviously you could have some achiral guys as well. Any questions on any of that stuff we talked about, I think, last time? Okay. So we are somewhere. We are here, hopefully. That's the solution. All right, so let's talk a little bit about the structures of the monosaccharides. As we talked about, typically, a lot of times these carbohydrates are written almost, if you want to think about it, like line structure, where just sort of those intersections are carbons. And usually we will put the most oxidized group on top. And in this case, that would be more like the functional group that we would see there on the top there. And in this case, once again, I will say 100% of the time, but a lot of times that last chirocarbon is right above that kind of CH2COH group. And again, it's not 100%, but a good amount of time. That is a lot of times your last chirocarbon. And once again, we see here the OH there is on the right, which gives us our D. OH group over here on the left gives us our L. And this is glyceraldehyde. And we always are looking for sort of the last chirocarbon from the oxidized group is sort of what we're looking for to make that determination. So it's usually down the road what we're looking for. This is very much how we write a lot of our carbohydrates like this, and our D and our L. The one that's a ketose will sometimes look a little bit different. Again, much like in organic chemistry, because it is 3 carbons that it sort of needs, you'll sometimes sort of see it written like that, where obviously this would be a carbon, right here would be a carbon, and right there would be a carbon. So it gives you that sort of 3 carbon run that you need for that ketone group. Sometimes they will also, just write the carbon in sometimes as well. So they'll sometimes do it like that and kind of put even 3 of them. Sometimes you'll see it written like that. So again, sometimes it'll just be sort of a line through here, and sometimes they will put the carbon, but you'll see that double bond. And much like an organic, you'll never find the double bond at the end here in the ketose because again, does need that 3 carbon run to do that. So here's some examples of some monosaccharides, D and L. And you should put a little star on this page. You should be familiar with these structures and the names that go with it. So this is glucose, and it's D-glucose because we got our last chirocarbon. Again, in this case, that would be a chirocarbon, that would be a chirocarbon, that would be a chirocarbon, and that would be a chirocarbon. So all those are chirocarbons. But again, the last one there that has the OH on the right would give us our D. In this case, this is ribose, which you also should be familiar with. 1, 2, and 3 chirocarbons, with the last one there being on the right. And this is galactose, 1 chirocarbon, 2, 3, and 4 chirocarbons as well. When I say be familiar with them, if you're laid up the structure, you should be able to maybe recognize it as glucose or something like that. You won't need to necessarily draw it from heart or anything like that. But if you are given the structure, you need to kind of associate it with glucose or ribose or galactose. Any questions on that there? So let's take a look at these, if they ever pop up, maybe. There we go. So we want to identify these as D or L. So take a moment and see what you come up with. Okay, so let's take a look. So once again, this is our most oxidized group, really the functional group. And we're looking for the last chirocarbon there from it, which would be that guy. And I see the OH on the left there, so an L for that guy. Same thing here. This is our oxidized group. Again, last chirocarbon from it would put us there. And once again, our OH is on the left. And this is our oxidized group up on top. And that would be over here, would be our last chirocarbon. And that would make that guy on the right there. Or the right, I guess it's not R. D would be better. It's right. It's all right. Yeah. This again was what I was just talking about. Again, we can see our ketone group here, carbon, carbon, oxygen, and carbon. So again, that kind of 3 carbon run. And again, that's sometimes how it is written. And obviously here's our aldehyde groups up here on each of these here. Question on any of those there? Hopefully they agree. They put D, not R. All right, I'm just kidding. All right, so let's talk a little bit closer about some of these monosaccharides. First off, it's glucose. Glucose is found in fruits, corn syrup. As we saw here, it's an aldohexose, which again, aldo means it has the aldehyde group. Hexose means it's got 6 total carbons, C6H12O6. We obviously use glucose for blood sugar, right? And goes through glycolysis, and again we store some of it for later use and stuff like that. It's obviously the monosaccharide in polymers of starch, cellulose, and glycogen. Glycogen is obviously the stored sort of sugar, if you will, that you could go through gluconeogenesis and break it back down and use it for some energy along the way. We can measure our blood glucose levels, and sometimes they do that right when you take a blood test. And if you're normal, you're in this range here. If you're hypoglycemic, hypo meaning less than, right? So not enough glucose in your body. And hyperglycemic means obviously you have too much, is not being really processed sort of correctly in your situation. Fructose is another carbohydrate here. It is a keto hexose. So again, it has 6 carbons and is the ketone group here. And it also is C6H12O6. It is what we find in fruit juices and honey. in the body, it can convert into glucose. I don't remember if fructose was on that other page, but you should be familiar with fructose as well. Again, the sort of the structure and the name that goes with it. Galactose, it's obtained from lactose, which is a disaccharide. So you could break it apart and sort of get galactose. It's very similar to glucose, except that it's got an OH there on carbon number 4. And we would number these carbons just like we would do in organic. So this guy would be carbon number 1, which is where their functional group would be. And then obviously 2, 3, 4, 5, and then 6 would be down there at the bottom. So here's our difference there between glucose and galactose there at carbon number 4. Yes, sir.
I'm just checking this real quick. The glucose and fructose, they both say they're in honey. So if you ask this question about which one's in honey, we just put down both.
So yeah, you could put both, I guess would be an answer on that. I don't know if I'd ask you that question per se, but yeah, either one would be acceptable in that case. Yeah. Other questions? Okay. So you're not going to have to draw fructose, so we'll just skip it. But again, you should be familiar with what the structure looks like. And again, this is kind of equivalent to line structure, if you will. All right. So let's talk a little about cyclic structures of monosaccharides. So our monosaccharides can sort of fold up, if you will, into sort of ring structures or cyclic structures. And they tend to make one of two sort of ring structures that we come across here. This is really a 5-carbon structure, but it kind of looks like our 6-carbon cyclohexane. This is a 4-carbon structure, which looks like our 5-carbon cyclopentane. The difference is there is a oxygen that is inserted into the ring. So obviously on cyclopentane and cyclohexane, they're all carbons on the ring. As it folds in on each other, the sort of straight chain, one of the oxygens gets incorporated into that ring. So we end up with kind of like a 5-member and a 4-member ring that occurs. So typically what will happen is a lot of times the hydroxyl group at carbon number 5 will react with the aldehyde group or the ketone group. The reaction is much like in organic chemistry, all kind of happening here to this guy. So to our carbonyl carbon is where it will sort of fold up on each other. You have your OH and it's going to kind of come in and react here. The result of that again is we will get a oxygen that gets incorporated into that ring as it sort of folds up on each other. So let's talk about these guys here. They do make a stable cyclic hemiacetal. If you remember, hemiacetal is a carbon that has a OH group on it and an oxygen carbon group as well. And for hexoses, the hydroxyl group on carbon 5 will react with it. But it's usually sort of the last chirocarbon that will kind of come in there and do the reacting with the carbon oxygen double bond. So a lot of times in a sort of a hexose or 6 of them, it's that 5th one that sort of comes in and does that. So let's talk about sort of how we go about drawing these guys. So let's just say we had this guy here. Just make one up. Why not? So let's say we had this made up carbohydrate here, and we'll do a little OH action there. We'll do an H. Do an OH. And why not? We'll do an OH there as well. So if we want to draw this guy into a ring structure, really sort of the first thing we're going to do is you can number the carbons so you can keep track of everybody. So once again, this would be 1, 2, 3, 4, 5, and 6. So we're going to take this guy and basically just kind of drop it on its side. So we're just going to take it and drop it down. And when you do that, if you take this guy and you just drop it straight down, we're going to get something that looks like this. And once again, this is going to be carbon number 1, which means 2, 3, 4, 5. I'll end up with this guy here. And again, that would be carbon 2 there, carbon 3, carbon 4, carbon 5, and carbon 6. Now, obviously, everything on the right-hand side will come down, right? So filling in our OHs and all that, we would have an OH here. We would have an OH there. We would have an H there and an OH there. Everything on the left-hand side, when it falls on its side, will then kind of go up, if you will. So we would have obviously the H here, the H here, the OH here, and the H here. So basically everybody on the right goes down and everybody on the left goes up. Any questions so far on that? So in this case, what's going to happen, since this is a hexose and really this guy right here is our last chirocarbon, this number 5 carbon is going to basically go and attack where the carbon oxygen double bond. That is going to pretty much make our ring that we need to draw. And you can figure out which ring you should draw based on pretty much how many carbons are there. So that is 1 carbon, that is 2 carbons, that is 3 carbons, that is 4 carbons, and that is 5 carbons. So the ring that we would want to draw is the 5 carbon ring, which really looks like cyclohexane, but again, it has a oxygen that's been incorporated in there. So it will look something like this, I hope. There we go. All right. Not my best drawing-ish, but something like that. All right, so we have our 5-member ring here. And one thing that we would see here is if we look at this guy, that is not part of the ring. And this is always what sort of happens is carbon number 6 here is really not part of that ring. It will always end up right above that and to the left of that oxygen. It will always end up right about there. So kind of to the left and above the ring is where that 6 carbon will end up. Any questions so far? Yes. Yeah. Yes. I'm sorry, say again, which ones? Mm-hmm. Yeah. Yeah, I just wrote backwards, so the carbon would be the one that's attached. It doesn't matter. I mean, it's the same thing as this. If this is what you're asking, it's the same thing. Is that what you're asking? Yeah. So I just kind of turned it around so the carbon is actually the correct sort of thing that's attaching, but it's the same thing, if that's your question. Yeah. And that's why, again, when I kind of went this way, I put it the same way, the CH2OH, so the carbon is the one that's attaching into the ring and stuff like that. You'll sometimes see people kind of draw like that, so the carbon, kind of shows the connection. Other question? And the 6 here is obviously just the numbering of the carbon. It's not, 6 carbons or anything like that. So now that we have this 6 carbon that's up on top, we could use it for our numbering purposes. This is going to be carbon number 6 that went up there on top. This then would be carbon number 5, and then we actually go counterclockwise here numbering. That would be carbon 4, 3, 2, and 1 in this particular case. So what is left at this point is to essentially just put our OHs onto this ring. And the deal is, because number 5 comes together with carbon number 1 in this case, we actually skip number 5 because, again, it gets incorporated really right there into the ring. So we then go to carbon number 4. And frankly, at this point, I can see at carbon number 4, my OH is up. So that is what I would draw. My OH would go up. At carbon number 3, my OH is down, which means I would draw it down. And at carbon number 2, my OH is also down, so I would draw this guy down. That leaves us the last one there. And you do have one of two options. You could draw the OH up. Alternative to that, just resketch that real quick. Let me do a better job. There we go. The other option is to obviously draw the OH down. And these are two what are known as anomers of each other. And one is the alpha and one is the beta anomer. So beta and alpha, depending on sort of, which way you draw that last one. So OH up and OH down there would get you either the alpha or beta, and they'll tell you sort of which one to draw. Question on that there. So the goal here when you do this is to take it, drop it on its side. You don't necessarily have to drop it on the side. If you remember that everybody on the right goes down and everybody on the left goes up, you could just leave it that way and do it as well, and make the ring that comes together. Let me see here. So as we can see here, we take this guy, we're going to drop it on its side, and we're going to then draw our ring. And once again, if we look on this guy here, it's going to be number 5 coming to number 1, which gives us 1, 2, 3, 4, and 5 carbons that are in that ring. So again, that is why they drew the 5 carbon ring. And again, going counterclockwise, skipping number 5, we kind of go back there. We can see that number 4 is down, 3 is up, and 2 is down. So that's kind of easy to remember there. So down, up, and down. On the other side of this line is really technically a hydrogen, but most people don't draw the hydrogen in. But that is technically what's at the other end of that line. So usually in these cases, they really will not kind of draw that in. And in this case, we have our beta, which goes up if it's the last carbon, our alpha anomer that comes down. And again, they'll kind of tell you draw the alpha or draw the beta version of this. And then that's what you would want to do. All right, so let me actually go back there. So why don't you try one here? Let's do bless you. So why don't you draw the alpha anomer of that guy? And then why don't you also do this one as well? So let me do this one. So you can do 2 of them here. Let's do all right, make up a couple here. And what you do for this, so I want you to draw the beta for this guy. All right, so take a couple of minutes to see what you come up with. Beta for this guy, draw the alpha for that guy. Looks right. Yeah. Okay, so once again, this would be carbon 1, carbon 2, carbon 3, carbon 4, carbon 5, and carbon 6. So if you like, you can drop it on its side, and we'll end up with 2, 3, 4, 5, and we'll have our guy at the end there. So this would be carbon 1, carbon 2, carbon 3, carbon 4, carbon 5, and carbon 6. Once again, everybody on the right-hand side goes down. So that's going to be OH, OH, H, and H. That means up here will be OH, OH, H, and H. This case is going to be this chirocarbon number 5 coming in to our double bonded carbon oxygen. And once again, you can just simply count up the carbons involved. So that's 1, 2, 3, 4, and 5 carbons. So that's definitely the kind of 6 carbon looking ring that has the oxygen involved there. Once again, this last group is going to end up up here, making that carbon 6, 5, 4, 3, 2, and 1. Again, we're going to skip number 5 as it gets incorporated into the ring. That brings us to number 4, where the OH is up. So we'll do a little up action there. 3, the OH is down. 2, the OH is down. And what's this, alpha or beta? This one's alpha. So alpha means that our last OH there should head down in that case. Yeah. Any questions on that particular one there? So looking at the next one, we got, so we'll redraw that one. So this one, we got this. And I think it's OH that way, I think. H, OH. All right. That looks like the right one, right? Okay. So we're going to, once again, if we like, drop this guy down, do a little deal like this. We're going to end up with this. We're going to end up with really, I'll draw the carbon in. You don't need to, but you got that double bond right there. And then you got 3, 4, 5. And again, our CH2OH at the end there. So this once again is our 1, 2, 3, 4, 5, 6 carbons. Once again, here it is going to be number 5, but it is going to actually, in this case, go to number 2, because that is where the carbon oxygen double bond is located. That means in this particular case, if we count carbons, we have 1, 2, 3, and only 4 carbons involved in the ring formation. So this is the one that kind of looks like cyclopentane that has the oxygen in there, which looks like this guy here. So this is why we would want to draw this particular ring here. We also see carbon number 6 there still stays in the same location, which would be there. And that would be carbon 6, which means this would be carbon 5. That would be carbon 4. That would be carbon 3. And that would be carbon 2. And carbon number 1 is also going to be off of the ring. As you can see there, it's, both of those circle things are not part of the ring. We'll do the same thing, except I didn't draw the rest of the OHs in there. That probably would have been helpful. So we are there H. So that's H, that's OH, and that's OH coming down that way. There you go. All right, now that we got everybody, just like before, we will skip number 5 and we will go to number 4 where we see the OH is down. We go to number 3, we see the OH is up. And this case, we were going to draw beta, I believe, right? So that beta means that the last OH, as I missed the carbon there, but the last OH would be right there. And that means on the other end of that OH should be this group right here, should end up there on that CH2OH, carbon number 1 in this case. So again, you can count your carbons, make sure you get the right number of rings. And in this case, with the ketone group, it's very common because it needs that 3 carbon run that you're going to end up with kind of 2 carbon groups there at the end that's going to be off of the ring. And that last carbon will be obviously off the ring. If we were drawing the alpha, everything would look the same, except the last one would just flip, right? The OH would go down, the CH2OH would go up in that case. Question on how to put these guys into ring. Yes. We skip carbon number 5 because it is where the ring comes in and closes and the oxygen gets incorporated into it. And technically speaking, it's there's actually just a hydrogen at the other end of that. And so we wouldn't put it there in that case. Yeah. It would. So it applied kind of similar, I think, here as well. Again, that's really a carbon, right? So it's got 3 lines coming in. So it's implied that there would be technically another hydrogen that would be in there. So we don't really draw it usually. There's too much the hydrogens in these things. So we usually just kind of focus on the OHs. But that is like the hydrogen that would be there. And then the oxygen gets kind of incorporated into the ring. And some of these other guys sort of leave as well. Some of the other oxygen kind of leaves off of the ring when the process kind of closes through the loss of like water. It comes out that way. On this one? Is that what you're asking?
Yeah, the left side, the left side is HHHO, and then on the right side is OH.
So on the left side here, HHOH, is that what you're asking?
Yeah.
And then on this side, it's OHOHH. Is that what you're asking? It's just really because the connection really is to the oxygen. So that's why I drew it like that. I mean, yeah, technically, if you wrote OH like this, it sort of implies that it is connected to the hydrogen, which it really isn't. So that's why sometimes people will kind of turn it around to show sort of the right connection to the oxygen. Kind of like the earlier question, why I kind of turned this guy around to show the connections actually to the carbon, rather than writing it maybe like what I did on the last one there, where you just kind of write it like this, where again, it may imply that, you know, it's connected to the hydrogen, which it really is not. It's actually connected to that carbon. So it's just kind of turning things around just to show the right connections. Other questions? Yeah. Yeah. The beta? Yeah. Oh, I'm sorry. This one? This one?
Yes, that one. So you put carbon 2
Uh-huh.
on top, the double bond line. Because didn't you say right goes down?
Oh yeah, it doesn't really matter in that. I could have drew it down or up. It doesn't. It's the functional group. So what really is important in terms of like right goes down and left goes up is the OHs, because that's really what you're going to use to determine where you should put those. Because the functional group, that carbonyl group, the carbon oxygen double bond gets kind of incorporated in the ring, it really doesn't matter which way you draw it, because you'll never need to look at it and go it's up or down for that particular one. But it does definitely make a difference for the OHs and all those guys. You know, that's the more important one. But yeah, you could have drew it the other way too. It's fine. Yeah. Other questions? All right, so clearly you need to be able to put these guys into rings and stuff. All right, let's go through here. We saw. All right. So this is the formation of cyclic glucose. And again, here's sort of how that whole incorporation occurs. We have our carbon number 5 with the OH group that comes in and really attacks the carbon oxygen double bond. And we get a little switch that sort of occurs. This H actually ends up coming out over here and making the OH group. So it all gets kind of incorporated that way. And as you can actually see on this structure, which was an earlier question, there is that hydrogen that we were talking about is right there. That again, not very often drawn in those rings and stuff like that. And this is our basically hemiacetal, right? We have a carbon that has an OH group and this oxygen carbon group that's attached, which is with that hemiacetal that we talked about as well. Glucose will kind of open and close into sort of different conformations, but most of the time it will stay in that sort of beta conformation on the right there, a little less in the alpha conformation as it sort of opens up and switches around. Here's fructose, which is similar to what we just drew. And once again, sometimes people always want to go to the first carbon, but the key to remember is it's that functional group is where it's going to close in on. And frankly, it's usually the last kind of chirocarbon is, again, what's going to close. And again, as we did there, you can just simply count how many carbons for really our options. It's either going to be this 4-member ring, or it's going to be that 5-member ring that you're going to draw. So that helps you decide which one you should do. And on either ring, carbon number 6 or that CH2OH group always ends up to the left and up off the ring. And then you can kind of use that to go backwards to number it. All right, why don't we draw one more here, see how you do. Okay, let's take a look. So we'll just number here 1, 2, 3, 4, 5, and 6. Once again, going to be number 5 here on this 6th guide. It's going to go to the carbon oxygen double bond, giving us really 1, 2, 3, 4, and 5. So that tells us we should draw really like our cyclohexane looking ring here. Once again, our number 6 is going to go up and above, giving us 6, 5, 4, 3, 2, and 1. I'm not going to drop it on the side. I'm just going to remember that right will go down, right, and left will go up. That means when I go to number 4, I got my OH that is left, which means it should go up. I got my 3, which is on the left there, should also go up. And this guy is on the right, which should go down. And my alpha means the last one should go up or down. It should go down. Yeah, so it should look something like that. Any questions on any of those there? Okay. I think you have the actual picture on the next slide. Actually, there it is. It agrees, so that's good. All right. All right, let's talk a little bit about some of the chemical properties of monosaccharides. Reducing sugars, good talk. Reducing sugars are monosaccharides that have that carbonyl group, which again is the carbon-oxygen double bond. That oxidizes to give a carboxylic acid. So it will undergo a reaction with Benedict's reagent to give the corresponding carboxylic acid. So if you remember, very much like in organic chemistry, if we oxidize our aldehyde, we get a carboxylic acid here. So pretty much all sugars are reducing sugars, including glucose, galactose, and fructose. They basically could go through that reaction that is there because they all have basically the hydrogen that's necessary to do so. So here's an example of that. Here's glucose, again, going through oxidation with Benedict's reagent, going to insert our oxygen right there to make really our carboxylic acid group that we see up here. And once again, the copper gets, excuse me, gets reduced from +2 to +1. And again, it turns out orangey red color, which I think you guys have seen in the lab. Obviously, if we do the opposite reaction, we get a reduction, involves the carbonyl group, and it will make a alcohol, basically. So very much like the other reaction, right? So these reactions are very much like what we saw in organic. Our primary alcohol, right, gets oxidized to an aldehyde that gets oxidized to a carboxylic acid. And obviously the reverse of all those would be the reduction reactions that occurs. It takes us from the carboxylic acid to our aldehyde to the alcohol. In this case, this would be like our carbohydrate starting place. So if we reduce that to the left there, we get an alcohol, which is sometimes referred to as a sugar alcohol because it comes from a sugar. And if we obviously reduce it from the carboxylic acid, we could get back to our sort of glucose. You're not going to be asked to draw any of those, but it's very similar to what we saw in organic chemistry. So here's those 3 together with an actual carbohydrate. And again, you won't be asked to draw it, but this is pretty much identical to what we saw in organic chemistry. Everything else stays the same. It's just that functional group part that sort of changes as it's oxidized. Really kind of, again, our alcohol to our aldehyde to our carboxylic acid as you go through there. So let's talk a little bit about disaccharides. Disaccharides consist of basically two monosaccharides that are put together. They are put together by, frankly, taking out water. So you take out water and you stick them together, basically. You do need to know, these are the three monosaccharides. We're going to look at each of them individually here in just a second, but you do need to know the three disaccharides, and you do need to know the monosaccharides that basically make those guys up. So what we'll see here, basically, if you put a couple glucoses together, take out some water, you get what is known as maltose, which is a disaccharide. If you take a glucose and a galactose and put it together, you will get lactose. And if you get glucose and fructose and put those guys together, you'll get sucrose, which is like sugar. And again, we're going to look at each of those, but you do need to know those three disaccharides, and again, the monosaccharides that make each of those up. So put a star next to it or something like that would be good. So let's take a look at each of these here. Maltose is a disaccharide known as malt sugar. It's composed of the two glucose units that's obtained by basically taking out water. It does form a special type of bond that you need to be aware of, and that bond forms when the water comes out that kind of groups those two guys together. This is what is known as a alpha 1,4 glycosidic bond, and we'll take a look at it on the next slide, the actual bond in just a second. And it is kind of what the name implies. It's basically a bond from carbon number 1 of one glucose, the alpha carbon, and the carbon number 4 on the other one. And that's what the 1 and 4 means. Basically, alpha 1 means it's the carbon number 1, that's the alpha anomer, and it's going to bond to number 4 there. It is found both in the alpha and beta form. So up on top here are two glucose guys. And if we do our numbering like we did just a second ago, 6 and going around counterclockwise, that puts us at number 1 right there for that particular glucose. Same thing starting at 6 here, coming around the horn here at number 4 there. That is the two guys that are going to come together. And it's going to be these guys that are going to come together to do that. We're going to basically just take out water, which is going to leave us one oxygen left. And that is the oxygen that binds both of those guys together. It forms this very distinctive looking bond, which, if you remember, alpha is down, right? So this bond looks like it is coming down. Yeah, so if you see that bond where it kind of comes down to an oxygen between two of these guys, that is the alpha. And again, it is alpha because this is the alpha carbon there, and that's carbon number 1. So that is why it is alpha 1, because that's where it comes from. This guy doesn't have an alpha beta, right? Because it's carbon number 4. Alpha or beta is only on that first carbon or that last carbon there. So that's why it is just alpha 1,4 glycosidic bond that occurs. So that is the bond that holds together maltose, those two glucose units, by taking water out. Clearly, if I wanted to break it back apart, I should put water back in, right? I put water back in, plops back apart into the individual glucoses. So again, you need to know maltose, two glucoses. It's held together specifically by the alpha 1,4 bond. You need to know that. You also need to be able to recognize it if you see it drawn in a picture like this, that is an alpha 1,4 bond. Any questions on that there? Okay. This is lactose. There you go. It's a disaccharide of beta D galactose and alpha or beta D glucose. So it's basically galactose and glucose. It is held together by a different bond. It is held together by what is known as a beta 1,4 glycosidic bond. It is the same sort of idea. This is our galactose here, and this is carbon number 1. And again, this OH is up, which is the beta, right? Up. And it is going to bond to our 4th guy over here, that OH. And this also makes sort of a distinctive kind of bond. It kind of looks like the O is going up. So that's a good way to remember it. Beta up, right? The other one kind of looks like it's coming down, which would be alpha. So again, this is our beta 1, 4 glycosidic bond. And again, water's coming out. So it is going to be that leftover O that's going to kind of hold those two guys together, which is this guy right here. Obviously found in milk and milk products. And some people have a problem with that little bond right there. And maybe a little intolerant there, lactose intolerant, to sort of break that. Any questions on that one there? Yes, sir. So once again, if your question is, you need to know that lactose is a disaccharide that's made up of a glucose and a galactose that's held together by a beta 1,4 glycosidic bond. And once again, if you happen to have just a random picture of something like this guy here, be able to look at it and identify it as a beta 1,4 bond. Yeah. Did I get your questions? Yeah. Yeah. Other questions for that? And lastly, the last disaccharide there is sugar. I guess we'll put it in like that, even though it's kind of all crunched together. Let's see what we can do here. So sugar is obtained from glucose and fructose, and it's held together by a different bond, which is the alpha beta 1,2 glycosidic bond. And in this case, we actually have both the alpha and the beta sort of involved here at carbon 1 and carbon 2. And that is because fructose is our kind of 4-member ring there. And again, glucose is our 6-member ring, where that obviously is 6, 5, 4, 3, 2, 1. And this is obviously up here 6, 5, 4, 3, 2. So alpha and beta kind of going up and down to each other, taking out everything like the water, and that oxygen leaves over is going to do that. In this case, we have both symbols because they are both on the end there, right, which gives us either our alpha or beta sort of connection that occurs there. There's maybe a prettier picture of what's going on here. So this one kind of goes straight up and down, but again, it's on both of those parts right there. And that gives us our alpha beta 1,2 glycosidic bond that holds that guy together. Question on that there. Also, just kind of going back here, this lactose, for example, is the alpha anomer. Again, the same reason here, the guy on the right here with the 1, obviously the OH is down. I don't know if they had a beta 1 drawn on one of these. I don't remember. They didn't. But obviously, if this OH was going up on that last one, it would be the beta version of maltose and so forth. Question on those 3. So once again, you need to know those 3 disaccharides. You need to know the individual monosaccharides that make it up, and you need to know the way to name the connection that holds them together. And again, they're all held together by that oxygen, which is made by taking out water, basically. Any questions on any of those there? Oops. All right, red structures are 2 monosaccharides and sucrose. We'll just take a look at it since you don't have to write it. And here's maybe a picture just not all sort of messed up here. Obviously, if we hydrolyze it, we're going to add water, and that's going to basically break these guys back into their monosaccharides. And once again, that OH here would be our alpha, and our OH coming here would be our beta. And once again, it is these 2 guys that are coming here to connect with the oxygen in the middle to make the guy, if we're going the other way, obviously, in this case. All right, I'm not going to talk too much about sweeteners. All right, so let's take a look at these. The monosaccharides that make up lactose is low glucose and galactose, perhaps, yeah. Maltose is a couple of glucoses. And sucrose, which is the last one we saw, is a glucose and a fructose, right? There we go. And this last day, I should say yes, but remind me in August. How's that? That's good. There you go. All right. So once again, this slide, you just start because frankly, you need to know that information that's here, right? And again, our lactose having the beta 1,4 connection, right? Our maltose having the alpha 1,4, and then our fructose having the alpha beta 1,2 connection that happens there. Any questions on disaccharides here? Now let's talk a little bit about polysaccharides. Polysaccharides are frankly really long chains of just glucoses together basically, and you take out water from each one and stick them together. So poly is a bunch of them together. They include amylose, amlopectin, starches made of D-glucoses, also glycogen as well, and cellulose in plants. So let's talk a little bit about each of these. We have amylose here, potatoes, I think. And it is actually this guy down here is amylose. And it is just a bunch of carbohydrates together, a bunch of glucoses together. And the difference with this guy is it is what is referred to as being unbranched. So like in organic chemistry, right, there's branches that come off everywhere. Here it's just really like a straight chain of glucoses together, gives you amylose. They're all held together by what we saw earlier, this bond, which is the alpha 1,4 bond, right, coming down. And that's the connection that we see here. Everywhere there's that connection, we basically took a water out to make that connection. Now we have amlopectin, which is basically the same deal. It is though branched, which means it's got the straight run of our glucoses here on the bottom, just like the other ones that has the same connection, our alpha 1,4 connection, bless you. But every so often it will branch off into a new connection here, which is our alpha 1,6 connection that actually occurs. Again, 1,6 between carbon number 1. Go this way. And carbon number 6 here, which is above the ring on the other one. And in this case, taking out our water like so, giving us our carbon 1 from this guy, carbon number 6 here. And again, it's going to do that alpha because of the carbon 1 coming down, and it's an alpha 1,6 connection. So they're both basically what we find there in potatoes, starches, but amylose is unbranched, so kind of just straight. Amlopectin is straight, and then every so often it's got the branching points. It's got the couple of different connections that occur. Any questions on that there? Yes, sir.
Would we see examples like background, or would be sucrose instead, or just?
It's just glucose in this case, if that's your question. So it's just glucose units that are basically just repeating over and over. So that's sort of the repeatable unit that we see in these guys, which is the glucose unit. So sucrose obviously is the glucose and the fructose together, so you won't see that in here. So what it branches out to is again more glucose units. So it's just where it kind of connects those two glucoses together is a little bit different. So amylose, as we saw there, is a polymer of alpha D glucose molecules. It's linked by that alpha 1,4 glycosidic bond. And like I said, the sort of distinction between that and the other one is it's a continuous unbranched sort of version. And our amlopectin, as we saw there in that last one, is, again, basically the same, except every so often we do get these branches to come off like the main chain. And we get that second connection at alpha 1,6. And again, there's still glucose all the way around in each of those guys. Any question on those two? Glycogen is the polysaccharide that stores alpha D glucose. So, as you go through glycolysis, I think when I was awake once, again, they use that for energy, and then leftover gets stored in muscle. I fell asleep, and then I woke up, and again they went through gluconeogenesis to pull that out and break it back down. It's like a Krebs cycle in there somewhere along the way, I suppose. But it is similar to amlopectin, but it's very much way highly branched. So there's a lot more branching that occurs in glycogen as it sort of gets stored in your muscle. Now, cellulose is a polysaccharide of glucose that is unbranched, but it does have that other sort of connection that we saw as well, that one that kind of goes up. So that makes me think beta when I see something that kind of is flowing upward like that. And that is our beta 1,4 glycosidic bond. Again, very similar to what we saw earlier. And that is the bond right there. And each of these guys, it cannot be digested by humans. So you probably shouldn't eat it, I suppose, because we cannot break down that beta 1,4 bond, which is probably why we don't eat the cotton, I suppose. All right. All right. So identified polysaccharides and types of glycosidic bonds. So obviously we have cellulose, which has that beta 1,4 bond. We have the amylose and amlopectin there in our potatoes, which has our alpha 1,4 for amylose and is unbranched. And our amlopectin is branched with the 1,4 alpha 1,4 and the alpha 1,6 as it branches up. And then obviously our glycogen is highly branched with the same connection as amlopectin, by the way. So these two guys have the same connection, but again, the glycogen is much, much highly kind of drugged out there. All right. Any questions on any of that there? Well, looks like that is it, I think. Yeah.